Okay, hello.
Yes.
It's
not related to I'm working.
Yeah. Oh, okay. Yeah, I think, yeah, okay. Sure, good idea. Okay, yes, well, yeah, we're probably really busy and, yeah,
And necessarily that there's some sort of companies and guidance that can make sense to
yeah, sure.
That's right.
I think if you
the officials again.
Yeah, I do. Yeah,
Just a mega
Do you want to do the introductions or shall I?
you can.
Oh, yeah. Sure. Okay. All right. Hello and welcome everyone. So today we've got three speakers and we're going to be talking about essentially current research, what's happening out there. And so the first person who's going to be talking is Zhenyang Shi, young to his friends, who's a third-year student at University of Queensland, who's studying, what do you study? Computer engineering. He's also an intern at ConsenSys. We've got Kamanashis Biswas, KB to his friends, and he's received PhD in ICT at Griffith University and a Masters of Computer Science, specialising in security engineering from Blekinge Institute of Technology, Sweden, and has worked as a faculty member from the Department of Computer Science and Engineering at Daffodil International University, Bangladesh. And currently he's an associate lecturer at Griffith University, and his research interests blockchain technology, design and development, lightweight cryptographic systems, and energy-efficient secure routing algorithms, intrusion detection systems, and clustering schemes in wireless sensor networks. And the third speaker is me. So I'm an applied cryptographer at ConsenSys. Got about, I don't know, heading towards 30 years experience. I've got an undergrad in engineering from QUT, an MBA from QUT, a master's from University of Wollongong. I went to the International Space University. I've been involved in blockchain for about 3 years. I've got a whole stack of patents, and I don't know, look at LinkedIn. So anyway, yeah, please take it away.
Cool. Thank you. Okay, cool. Thanks for coming, everyone. I just, yeah, so. Yeah. So my name is Zhenyang Shi, or just call me out will be good. And I'm an intern at ConsenSys and within the PEXS team right now. And as we know, public chain Ethereum is a decentralized peer-to-peer network of untrusted nodes that execute transactions, share and agree on the same view of data, the world state. They use DevP2P stack to discover peers, establish secure communication channels, exchange data, and reach consensus. So I believe most of you coming to the presentation today, or at least some of you, are Ethereum developers. And usually, when your work gets closer and closer to the protocol stack, you'll find it becomes quite difficult to debug your project or just to test its performance. So therefore, in the past 2 months, I was working on a Wireshark dissector for the DevP2P protocol, together with another intern named Scott, who, by the way, is also an UQ undergrad student. And the Wireshark is a free and open source packet analyzer used for network troubleshooting, analyzing, and communication protocol development. And the Wireshark dissector is just a protocol parser that registers itself onto the Wireshark environment, gets called to analyze packet data, and publish the result as a structured tree to present to the user. So for the DevP2P dissectors, we are developing 2 other dissectors. The first one is a UDP-based DevP2P node discovery protocol dissector, and the second one is a TCP-based DevP2P wire protocol dissector. So as of today, we are pretty much finished the development of the first UDP dissector. So yeah, I do a little bit demo today. But before I demo, I just quickly go through the node discovery protocol. So there are 4 types of packets in the node discovery protocol. The first one is ping packet, POM packet, find node packet, and neighbors packet. So the ping and the POM packet are a pair of messages to initiate bonding process. The same for find node and neighbors. They are also a pair of messages to explore neighbors nodes. And all the packets are sent with recursive length prefix encoding, so IRP encoding, which is just an encoding algorithm used by the Ethereum. I was supposed to do a live demo on my laptop today, but unfortunately the display laptop is kind of fixed. So what I'll do is I'll show some of the screenshots and maybe play some of the demo videos.
The video is up on YouTube.
Okay, it's up on YouTube as well. So this is what it looks like when Wireshark captures some of the packets from an Ethereum client. And as you can see, all the data are in hex format. It is quite difficult for us to figure out what is actually going on here. And this is what happens when we add the dissector to the Wireshark. So as you can see, it analyzes each of the packets and recognize their packet type and display all the information with human readable text. And let's start with the ping packet. So this is a sample ping packet. This is what it looks like before I add the dissector. As you see, all the data are in bytes, very hard to understand. And after I add the dissector to it, it analyzes the packet data, and so we can have a clear idea what the packet is. For example, this ping packet has a version of 4, and its sender's IP, sender's UDP TCP port, receiver's IP, receiver's UDP port, all that stuff. So when a node receives the ping packet, it will respond with a POM packet. So this is a raw POM packet, or in bytes format. And after I add the dissector to it, it displays all the information contained in this POM packet. So the receiver's IP, UDP TCP port, and the hash of the ping it is responding to. The same for final node. So before and after. There is a target public key contained in each of the final node packet. So what is happened is when a node receives a final node packet, it will respond with a neighbor's packet containing 16 closest nodes to the target node in its local table. And so that's for the neighbor's packet, raw message. And after we add the dissector, all the data is being dissected into a list of nodes, and of course we can check the information of each node. So it's IP address, UDP TCP port, the ID of this node, which is just the public key of this node. And of course you can apply different filters to the packets you captured. For example, if you only are interested in the ping packet, you can apply this filter, and only ping packet will be displayed. Or maybe you just want to check if there's any ping packets whose sender's UDP is not bound to the default 3033. You can apply this filter and to get rid of all other packets. Or maybe you just want to find out if there's any neighbor's packet containing less than 5 nodes. This is the filter you're going to use. So actually there's a lot of filters coming together with this dissector, and it will be very helpful to use filters when you only interested in some particular packets. It also comes with statistics of the packets you captured, so which can access over here. So statistics, Ethereum DevP2P, and packet stats. Here you can get a clear idea of like how many different packets are transmitted each type, and the frequency of the packets each type per node as well. What's more, so node discover messages are just like RPC style exchanges. So ping is sort of like a request and to the POM, final node to the neighbors. And with this dissector, you can display each of these conversations in a conversation view. So there is a section called conversation ID, which is just the ID given by the dissector to like indicate a unique conversation. You just right click on that, apply the filter, and all the packets will be displayed in that conversation. So at the bottom of the window, you can see how many different types of packets are transmitted in this unique conversation. And on the top left corner, the little arrow over here is an indicator of the request and the response. Of course, there's a response time displayed at the bottom of the window. For the response time, it has also been added to the stats as well. So what you're going to do is just click stats, response time, and select Ethereum DevP2P discovery, and you can find out what's the minimum response time of like a ping to POM, or the maximum response time, or the average response time. And actually, I do have a video. I do have a video here. Yeah, it's just a small live demo, which I'm gonna play here. Hopefully, it works.
This is a live demo for Wireshark DevP2P node discovery dissector. The first thing I will do is I'll start Ethereum client, and then I'll capture over Wi-Fi. And you can see it recognizes all the DevP2P discovery messages, print the packet type, it recognize different conversations, error messages based on types. This is a ping message. All information displayed, sender's IP, sender's UDP port, TCP port, receiver's IP, receiver's UDP port. This is a home message. It also has all the information. Same for find node and neighbors message. For neighbors message, you get a list of neighbors nodes. And in each node, you get the information about this node. So its IP, its port, and its public key. At the bottom, you can see how many nodes are included in this message. And we can see one of the conversations. For example, the conversation 342, we right-click on that, apply as filter. We can see how messages being paired. So this ping is paired with this pong, and this ping is paired with this pong, and this find node is paired with this neighbor's message. And there is also a response time. So P2P response time, F2N response time, so ping to home and find node to neighbor. There is a stats about this dissector, about these packets. So select statistics, Ethereum DevP2P pack stats, and you can see how many packets are transmit. So number of phones, number of pings, and different messages. And you can also see the frequency of different types of messages per node. There is also a service response time accessed over here. The ping to pong response time, the minimum is this, and the maximum response time, and the average response time, the same for find node to neighbors.
Cool. So at this stage, we are pretty much like finalizing this dissector. We're finalizing this dissector, including all the install instructions for major platforms. We have already support Windows, and we almost finished the support for macOS and Linux in the coming few weeks. And after that, we will make this dissector open source, so everyone could have access to it. And after we finish that, we will work on the TCP-based protocol dissector. So please follow us, follow Pegasus on Twitter. That's where you get the update. Yeah. Thanks for listening. Any questions? Yeah.
So currently, currently Wireshark doesn't come with any support for Ethereum protocol. You have to develop everything yourself.
Yes, that's right. Yeah. So basically, I implement all the IRP decoding and just analyze the node discovery protocol here. And, yeah.
What sort of work is involved in supporting all those different platforms like that?
It's basically just a building, just a making, just a compiling. Yeah. Yeah. Any other question? Yep.
I don't know the protocol that well, but what goes wrong that causes you to have to do this kind of diagnosis with the protocol? Does it the networks fail, or nodes go down and you can't find the node again, or what's the story?
Sorry? What is the purpose of this?
Yeah, well, what goes wrong in an Ethereum network that causes you to have to do this kind of diagnosis?
It's just we are doing a project, and it just when the project gets closer and closer, deeper and deeper to the protocol stack, it's kind of difficult to test its performance, like the response time, all that stuff. That's mainly motivation we are doing this project, the dissector. Yeah.
So most of the time in an Ethereum network, it's going to be running and it's going to work fine. You're not going to need this kind of tool.
No.
It's going to be like, I guess, like Yang was saying, it's for the devs that were kind of developing the actual a new Ethereum client and wanting to understand the protocol. And thought, hey, having Wireshark and being able to read things nicely through here would be really useful. Yeah, so that's what sort of drives it.
Yeah. Any other questions? No? Cool. Yeah. Thanks again for listening. Yeah. Thanks. Yeah. Hand over to you.
Forwards and backs.
Okay, good afternoon everyone, and thanks Peter for inviting to this meetup group. So this presentation is based on one of our paper which is published in FTC 2017 last year. So as you can see from the title, this is basically an application of blockchain. So what I'm going to present here, not that much technical, but definitely covers a very interesting area of supply chain, which is basically one of the main problem in many disciplines. So, and every month we can see there are a number of papers which are published on supply chain, and they are using different mechanisms, and some of them they are basically looking to the blockchain. So how we can implement or integrate blockchain with the traditional or conventional system so that we can efficiently handle different products or different entities in the whole supply chain. This is the outline. First, I'll be talking about wine counterfeiting, then different entities in the supply chain, and also the traceability system. How actually we can trace a wine bottle, a particular wine bottle. What is the origin of that wine bottle? What is the provenance? What is the history? That which different entities handled this bottle, and what was the temperature? What was the different processes like the fermentation, decantation process, all those things there. Then blockchain technology. So I guess I don't need to go through that part because everyone in this room, I'm pretty much sure that have very good understanding on blockchain. Then blockchain-based traceability system. There's a system we wanted to implement, and we implemented it using the multi-chain platform. So we'll also show you product implementations that we did using the multi-chain. And then finally I will conclude the presentation. So wine counterfeiting, so it is one of the most critical problem in wine industry because every year they lose about 15 billion US dollars for wine counterfeiting or wine fraud. So it's basically about 5% in the secondary market, which means about 5% of the wine which is sold in the secondary market, they are basically fake wine. So that's why everyone is looking in this problem, and most probably you have seen one of the solution recently, so which is using Bitcoin for each and every wine bottle, just fraction of the Bitcoin that would be used for uniquely identify each and every wine bottle. So the wine fraud, it comes actually in two ways. One is relabeling, so which means that most of us, we don't know. We just know about the name of the wine, but we can't remember what is the labeling of that one. So that's why we can, the people, they can relabel it and they can sell it to the people who doesn't know that exactly whether it is real or fake. And the other one is that legitimate bottle can be refilled with cheaper wine. So what we can do, we should have a traceability systems which say that whether this bottle of wine has been sold or not. We can check that one and we can see, okay, if it is already sold, no one can sell it again. These are the entities in the wine supply chain. So here we have the grape growers, so who is responsible for producing the grape, and then all other information like the pesticides, fertilizers they have used, that like the temperature which is maintained during this grape growing, which vineyards they have used, what is the geolocation of that vineyards, all those information they can keep in the blockchain. And then we have the wine producer, which is responsible for producing the wine, and it goes through a number of procedures like fermentation, decantation, all those different procedures, and then they can directly sell it to the filler or packer, or they can sell it to the bulk distributor. So there are two different processes. Some wineries they directly sell it to the filler or packer, or they send it to the bulk distributor. It goes to the transit seller, and then it comes to the filler or packer. Then it goes to the finished goods distributor, and then the finished goods distributor goes to the wholesaler and the retailer. So finally it comes to the consumer. So here are two different entities. Some of these entities are internal entities that I already described, and the top entities like the supplier, freight operator, importer, they are the external entities. So what we can do, we can put all the information in the blockchain so that we can easily trace from which part or from which entity this product or this particular element is coming to the next entity. Now, current traceability system, so they're basically using different mechanisms like barcode, RFID, QR code, and EPC. And there are many problems with all those systems. Some of those levels, they are not actually reliable because sometimes they're just damaged, and some of the modules, they don't work in real time, and there is no way to monitoring the temperature. But in some cases, temperature is also very important, like in the fermentation procedure. So that's why it's actually problematic to keep the record of whole procedure, since it is very complex procedure and lots of entities are involved in this procedure. So authenticity of the information is really a problem because there are many steps which are not validated, which is not verified by anyone. The other thing is that fake history, we can provide the fake provenance history there because it's a centralized system and the industry is maintaining that centralized system, so they can put the information whatever they want in that in their system. So what we can do, so we are saying that we can use blockchain to get rid of these two problems. Now, this is about the blockchain technology. I'm not going through this one. In most of my presentation, I put this slide, why blockchain? Because people say that programmers, they don't have sense of humor in that way that the general people have. But that's wrong. Because if you look on this side, so this is one of the conversation between the hackers or between the group, ThunderCrypt group, which is basically made the ransomware WannaCrypt last year or year before most probably. So most of the people that ransomware actually encrypted the files of most of the computers, and then UK hospitals, they were one of the target for massive ransomware attack. So one of the Taiwanese guy, so his computer also attacked and all his files encrypted. He just sent a message that my monthly income only $400. You really want to do this on me? So then they replied, the hackers of the groups, ThunderCrypt group, they replied that they overestimated the income for Taiwan. And so, okay, you don't have to pay now. We have switched ThunderCrypt to decryption mode, blah, blah, blah. And you can see the message. But if you indeed like something about ThunderCrypt and would like to donate us a few cups of coffee, always feel free to do so, and then the public key. So, yeah. So I always use this slide in most of the presentation because I know that we are the programmers, yes, they have really the tough time. Most probably you better know it, how many nights you are working without any sleeping or a couple of hours sleeping. Yeah, but still we have good sense of humor, right? Okay, so blockchain-based traceability system. So in this traceability system, what we have different entities. So these are the different entities that we have in the supply chain: grape growers, wine producers, and so on. So each of them, they can create blocks using list of transactions they want to put it there. So, and these blocks has to be verified, as we know, and then it will be added into the chain. And each of these blocks, they contain different information like the ID of entity, then batch number, then the dates when they are collecting or when they are sending it to the retailers, something like that. All the information will be collected there. And here we can see in this block we have 8 entities, and five of them are basically the miners. But it depends how you are implementing the system, because you can use the private blockchain, you can use the public blockchain. I'll come to that part. So what exactly we have done here? So in this case, we have two things. We have the batch number and we have the unique ID for each bottle of wine. Because if we have a wine producer, they are actually producing different batches of wine. So which means that we uniquely need to identify each batch of wine, and also we need to identify each bottle of wine. So that's why it's a combination of batch ID and the bottle ID, so that we can uniquely identify each and every wine which is sold to the consumer. So, and this ID can be used, so we have a front end. Using that front end we have designed, so we can put the bottle ID which is on the level of the bottle, and then we can see what is the history of that that wine bottle, that from which vineyard these grapes have been collected, who was the producer, who was the bulk distributor, which time actually they transported, what is the temperature. All those details information, it would be shown from the grape growers to the consumer end. So yeah, this is the implementation platform that we have used to implement our proposed system. One is this is the multi-chain platform. I'm not sure is anyone familiar with this platform, multi-chain platform. No, yeah, it's not actually that much used. It is a private blockchain. So and it's based on the Bitcoin platform. So but it is open source, anyone can use, definitely download and just can use it. It uses streams functionality, so which means that you can have multiple streams. Although we didn't use multiple streams, we just used only one stream. But the good thing is that you can implement multiple streams. So for example, if I am a wine producer and I am buying grapes from different grape growers, so which means that I can maintain different streams for each and every different grape growers. So it's a bit good, because when you are searching for information at that time, you don't need to search each and every stream. You can just search for a particular stream, so which is corresponding to that particular product. So that's a good idea for multi-chain, because it actually enables multiple blockchains you can simultaneously create. And in our implementation, we basically used 5 entities. One is grape grower, one is wine producer, bulk distributor, then filler or packer, and the retailer. And 3 of them, wine producer, bulk distributor, and filler and packer, we assigned them as miners. So all entities, they basically generate the blocks in forms of transactions. They have the transactions, put it into the blocks, and then sends the blocks to every participants in the blockchain. The miners verify it, and then it is added to the chain. So this one is the multi-chain streams that we have created. These are the 5 entities. You definitely know about this, because this list shows that those 5 entities, and these are the public key of all those entities. Each and every entity is defined by their public key, which is basically also called address of each and every entity or creator. And then this is the transaction. So this is one of the transaction which is included in block 581. So as we know, every block can have more than one transaction. It depends. So this is the transaction. This is the creators of the hash of the creators, and this is on the multi-chain WSC, because we created this multi-chain WSC when supply chain. And this is the block that we have created, and this is the block created by the grape grower. So when the grape grower is putting the information, so it's added in this block. And this is the block. So previous one, this is the transaction, and this one is the block. Sorry. Yep. So this is the block, and you can see in this block actually we have two transactions. One is that one that we have seen here, this one. The other one, I don't know. So this is the one. The bottom one is the one that actually put by the grave growers. The other one of the problem with multi-chain is that when you are running the multi-chain, it will automatically generate some of the transactions, and we don't know what is those transaction contains. So, but the good thing is that when you are linking back at that time, those transactions, it doesn't make any sense, or it doesn't show you when you are getting all those transactions out at that time. It will only show those transactions that you entered in the chain. So, but when you are running the multi-chain, it automatically creates two streams. One is root stream, another one is root stream. In the root stream, it's always putting some transactions there. So this is the traceback capability. So as we said before, we have unique bottle ID there, which is actually combined with the batch ID. So when we trace back using this bottle ID, WB001, so it is not sold because sold equals to 0 is still. And then from that bottle ID, it gets back the bulk distributor, then it goes back to the wine producer, and it goes back to the grape growers, and it goes back to the origin of that vineyards. So all those information can be actually shown from this when you are tracing back using just the ID number. So here we didn't put details because in each and every step you can put all those detailed information and you can go back. For example, here we have just showing it here. This is the origin, this is the type of vine, this is the treatments which is used for that particular vineyard. We just put all those information. We didn't put the other information, but you can see each and every information that you are putting in each and every step by different entities there. So one important thing what we can do here, if a bottle of wine is sold at that time, we can, this actually have not been done, but I am saying that we can do, I was thinking that we can also do in this way. When a bottle of wine is sold at that time, we can just run a smart contract, which would actually trace back all those information and put it into another block. So in this way, each and every bottle of wine, when it is sold, will have a block that, okay, this bottle has been sold. So when you are tracing back at that time, you don't need to trace back to each and every transactions. For example, a bottle is not sold. I can just check on that sold one. If it is not there, that means it is not sold. If it is sold, definitely I will find the records from there. So most probably that would be a bit efficient way if we are tracing back. Here we didn't implement that one. So we are actually thinking about, because there are many other applications of supply chain, like currently we are working on vaccine supply chain. So there, yes, definitely we are implementing their smart contracts because temperature is very important for vaccine supply chain. All the vaccines, most of the vaccines, they must be kept in temperature between 2 degree to 8 degree Celsius. So which means that if this temperature, if the vaccine is stored not within this certain temperature range, immediately it will generate an alert, and every system or every participants in that system, they will know that, okay, this vaccine is not safe to consume. So here also the same thing we could do, so which would be very efficient in that sense. So definitely it is safe and secure and transparent system, and it provides greater traceability. We can easily see who is the origin, what was the vineyard used, and what are the pesticides used. All those information we can see, the total procedures, and cost-effective solution if we compare with the RFID or the other methods that we are using. Just shortly want to introduce our blockchain research group, because yes, we collaborate with many other people in industry. So if you are interested, you might find anyone who is closely working in your area. So Associate Professor Muthu, so he's working on mainly cryptocurrency, also legal aspects of the blockchain, but he has also knowledge in other areas definitely. Professor Jinsong is working on verification of smart contracts. So he has his own tool, which is used by about 170 institutes all around the world, PET. He is using PET to analyze the source code of the smart contracts and to verify whether this smart contract has some vulnerabilities or not. Zhenyang, he's basically looking on the security issues of the blockchain. So he has many protocols. He developed or designed many protocols, lightweight protocols for key exchange mechanism, but not for the blockchain, for the wireless systems and others network. So he's working on that area. So William and I, we are mainly working on multiple areas. Most of them are basically application based. So like the Vexi chain, smart internet pricing, rental history check, public trustees, all those things. Yep. And we have 10 postgraduate students who are working on different projects and 6 undergraduate students. It is really impressive that 6 undergraduate students, they are working on blockchain and they have very pretty good idea in this area. So yes, people from the undergrad bachelor levels, they are also working in this area. That's very good. Thank you very much. If you have any question. We use Ethereum for Vexi chain, according to that's another one. But here we use the multi-chain. So multi-chain is a private network, private blockchain basically. We didn't implement in public blockchain. Yeah.
How do you enforce trust in information provided by large organizations or entities that have built the supply chain and therefore own the grower, the producer, the distributor? How do you make sure that they don't upload false information to them?
Yeah, that's a big problem with the private blockchain. So when you are using the private blockchain, so the miners, they are basically pre-selected and definitely we are trusting them. So yeah, since here we have the miners like grape growers, they are putting the information which is false information. So the miners are, in this case I guess, yeah, wine producer, bulk distributor, and filler and packer. So yeah, they can check those information because they have to sign that one. So if they approve that at that time, it is possible. But that's the problem with the private blockchain because we are trusting the miners which are pre-selected.
Surely it would be an issue with both public and private blockchains, right?
Yeah, definitely.
So how do you build the technology, then how would you enforce it? How would you enforce the trust behind the technology?
What about reputation? I mean, if you're in some supply chain and you sign something that's dodgy, your reputation's gone.
Yeah.
So, and maybe there would be legal recourse. You know, you've essentially, you know, signed something saying this is valid, real wine, and you've done something, you'll end up in court.
Yeah.
Yeah, in some cases we can also do it in different way, like if we use some smart contracts, we'll check all the conditions before approving a block. So it has happened in some cases. I just reviewed a paper and they came up with their idea that at the top of the blockchain, we have another blockchain, which is basically the smart contracts. So when two entities, they are making the transaction, it will come to that smart contracts. It will check all the requirements. If they are fulfilled, all the information goes with, aligned with their claim, then they will put it into the blockchain. So they will generate the hash and then they will send it to the upper level, otherwise they will not. So that's a good idea actually to enforce trust that okay, we have some sort of okay. So thank you very much. Yeah.
Sorry, what did you say was the identifier on the bottle? So like if I buy a bottle,
Right.
I don't wanna. What's the identifier that identifies that specific bottle
Right.
that I can see?
Yeah. So if you buy a bottle, in that bottle you have unique ID and batch number. So we have an application, it's mobile applications or web applications. If you are putting that number of scanning that one, so immediately it will show that whether this bottle is sold. If it is sold, when it is sold, and all the information regarding this bottle. So,
so if I copy that whole label as it is, and the original bottle isn't sold, how do I know whether it's a fake bottle or the real one?
If you copy the whole thing, it means that you have to copy it from the retailer, right?
Yeah, I buy the bottle. Okay, then
if you buy the bottle, at that time the information is already there.
But what if I just copy the thing? So you say it's just a code. I can just have a template and put that code on a fake bottle, right? Without buying it. So how do I verify that whether it's a fake whether it's the fake or the original?
One thing is that if you can copy those code and everything from the retailers as sold,
Yeah.
so then it is possible in that case, because that is not sold yet, right?
Yeah.
So yeah, if you don't have that level exactly, then it is not possible.
Except if you add the retailer to the whole supply chain. Then
Retailer is
I
also
know
integrated in
that
supply
if I
chain.
buy it from anywhere else, then the actual end retailer, then I have.
Yeah.
Yep.
Retailers are also part of the supply
Okay.
chain. So that means that when a bottle is sold, at that time the retailer has to input that this bottle has been sold, this is the place,
Correct.
this is the time, all those things.
Wouldn't necessarily need to involve the retailer because the retailer would reorder from the distributor.
Yeah.
And presumably within a day or two, the previous batch would have been sold.
Yes, yes.
When I work for wine provider, and this is a real problem, especially for cheaper wines that are not used to authentic.
Yeah, but that's a good question. We didn't think in that way that okay, so the bottle can be at the, for example, in a shop, and someone just used the mobile and then took the picture and then using the same but still it is not sold. So which means that if someone is selling that one, he will say that okay, it is not sold. Yeah.
Yeah, as long as the original is not sold, you can sell a fake bottle with the label, but first only once, and you can't copy it 100 times.
But
you can
again,
just buy the good bottle, drink it for yourself, and sell the label with the cheap one. But that's only a one-off thing. You can't make 100 copies.
We can do another thing. We can also put the information that okay, so this bottle is actually delivered to this retailer.
exactly.
Okay, so we can also put that information. So if someone is selling that one, then we can check that. Okay, so most probably they have bought it from there, so you can check it if that retailer, particular retailer, you can put that information. I guess that's all right. Thank you very much.
Okay, thank you, KB. Okay, so hello. So I'm going to talk about Ethereum private sidechains. So I'm doing a part-time PhD as well as working full-time at ConsenSys, and I've changed my PhD topic so it actually coincides with what I'm doing at ConsenSys, because that's making my life much easier. Far more likely to actually finish the PhD. And so my research essentially proposes Ethereum's private sidechains. And what I'll do is I'll walk you through an example which will help introduce the whole area, because otherwise it's a little bit abstract. So imagine we've got a management chain, which could be Ethereum mainnet, but it could just be a consortium chain. And imagine we've got separate blockchains, which we're going to call sidechains, so parallel chains of, so that they're essentially the same as an Ethereum blockchain, but in parallel. And so one of them, it might have an oracle on it, and so maybe that provides some sort of information like, say, exchange rate information. And in fact, you could even imagine that you could own a company and you could get that information and you could be deemed a good source of that information, and you could get people to pay to access your blockchain. You know, you could authorize people, and you could say, if you give me so much money per month, I'll authorize you to access my sidechain. And maybe there's a government department which runs a land registry, and so maybe they run a blockchain. And so maybe on each of these, maybe you've got a management and pinning contract which helps coordinate activities on sidechains, and that's on the mainnet. And then maybe you've got an exchange rate Oracle smart contract which is sitting on the exchange Oracle contract, Oracle sidechain. And maybe you've got your Department of Lands or something like that. Some government agency have got their own sidechain and they've got their land registry contract. And so entity A, it gets some configuration information from somewhere. Now, I've got a few good ideas on how you can do that, but at the moment, most people, how they do it, and most blockchain platforms, they have a file, essentially, that has to be distributed out of band. So A instantiates the blockchain, so this sidechain, so it sets it up, and it registers the sidechain with the management and pinning contract, and it invites these other entities, B, C, and Q, to that sidechain and registers their participation in the management contract. And so it then, deploys a contract. So it does a transaction which deploys a contract, and maybe it's for a house purchase. So you're buying a house, and maybe A is your lawyers who are acting for you, who are, you're the purchaser, and maybe B is the seller, maybe, and maybe, C is the bank. Maybe you've got multiple parties involved. But, though I'm talking house purchases, this could be anything, really. And so maybe A does a transaction, and maybe it needs to read the state. So it does a view call to a smart contract on a different sidechain, for instance, the Oracle. And maybe B does a view, and then maybe C it does a transaction, so it updates the state. So you'll interact. These parties are interacting with that smart contract, and importantly, though, A has done something which has caused a read from a different sidechain. And then maybe you've got Q as well, and it might say read the overall state of the sidechain, so essentially the block hash, and then it might pin that to the management and pinning contract, in that way sort of locking in the state of this sidechain into the main chain, so that you can't back out of it. You've locked that state in. You've got finality. And maybe you could even set it up so that Q can only see the encrypted state of this blockchain, not the plain text. So it can pin the state of the blockchain, but it doesn't know what's actually happening in the blockchain. And that's possible too. And that's desirable. You might want to have an observer, like the Reserve Bank might want to be able to observe what's going on in blockchains, but it might not want to, so you might have a regulator, and they might need to see that stuff's happening, but not actually need to know the details. That's possible. And then maybe what you might want to also do is add extra parties to the sidechain. And so maybe there's a voting mechanism, and so maybe the C and Q, they're unmasked participants. So maybe A and B are masked participants. So no one knows that they're actually on the sidechain, but C and Q are public. So they're they're operating on the sidechain, and they're known to be there are known to be two parties, but because of how they're masked, no one knows who they are. And so maybe C and Q can do some sort of voting mechanism such that they add D to the sidechain. And then maybe D does a transaction on that contract which causes a transaction on the land registry. So in other words, D might be a government official who says, okay, it's all done, you've bought the house, you've come to an agreement, okay, I'm going to push this through to the land registry and update the land registry so that the party has gone from this person to that person, as an example. And so that's been at a certain level of abstraction where we've been talking about side chains. But another way of looking at Ethereum is nodes. And so when we look at an Ethereum network, you've got a whole set of nodes. And in fact, maybe the pinky ones belong to one company, and maybe the yellow ones belong to a different company. And so maybe A, when it's doing all its transactions, it's actually interacting with the pink nodes, because, they're a member of company A. So when you're on a private blockchain, all nodes aren't equal, because maybe only the pink nodes and the yellow nodes and the blue nodes are supposed to have access to this blockchain, not all of them. So that's another thing to be thinking about, another level, another way of thinking about things. And so another thing to think about as well, another different level of abstraction, is the software behind it and how that might work. And you might have a software architecture that might look like this, where maybe you've got your main net and essentially your normal Ethereum client, and then in parallel with that, you might have a whole host of sidechain clients which operate on sidechains and are able to either operate in the same process or in parallel processes on the same computer, but maybe they operate in different computers. And so you need to maybe have the ability to spin these up on the fly, because we could say that we spun up a sidechain on the fly, so you're going to need to spin up an Ethereum or a sidechain client on the fly and add other users to it, to the sidechain. So we've looked at an example, but what are the requirements that are coming out of this? What do you actually need to be able to do to deliver this? And so permissioning is one big thing. So you need to be able to essentially permission around the API, like who can establish the sidechain. So when you did the API call saying, hey, set up a sidechain, you're probably going to want to limit who's allowed to do that. And equally, when you're doing transactions on the sidechain, you're going to want to limit who's allowed to do which transaction, what types of transactions. Also, maybe you've got, as a node, maybe you've got an incoming sidechain establishment request. And you might say, well, I'm only whitelisting certain addresses that can set up a sidechain, or maybe I'm whitelisting everyone and blacklisting a few. Also, once you're on a network, there are only certain nodes that should be allowed to contact you because there's only permission nodes on that private network. We've also got privacy. You know, the list of people involved in, say, that house contract, maybe you don't come to an agreement on the house sale and, you know, for some reason or other it falls apart. Why should everyone know about the fact that you're even going to do it? Maybe that contract was for something else, like, say, I don't know, a supply chain or gambling or something else, something that, you know, you don't necessarily want the world to know about. You don't want everyone to know that you were participating in that. You might be happy for people to know the result, but not whilst you're doing the negotiation. So the list of participants needs to be hidden. The rate of transactions needs to be hidden. You don't necessarily, you know, information can be derived from the rate of transactions that you might be doing. Maybe you want to shield the identity of the sender of a transaction, and maybe you want to shield the balances that are involved. You need a mechanism to bootstrap the system as well. But how do you know, if I'm going to, say, do a network with Scott and Yang, I don't want to have to share a file that's got IP addresses and encryption keys. I want something nice and easy, like their domain names that they're prepared to use, something like that. We need a voting mechanism or some way to add and remove participants. And we need a way of anonymously doing pinning back to the main chain. Also, you notice that there was some cross-chain stuff. And can I tell you for free, cross-chain communication is by far the most complicated bit of this, by about 1,000,000 miles. So you need to do cross-chain, I think, and for viewing and writing. And that there are various sub requirements around that about participating nodes and non-participating nodes. But so anyway, that cross-chain is something that's very much needed. And then you need to have an Ethereum EVM because though there are alternatives, I think at the end of the day, a lot of people know Solidity, a lot of people want to use Ethereum. So whatever solution, at least I'm coming up with, I'm going to have an Ethereum EVM as its core. And you need to have a shared state, which I know everyone's saying, hey, we're in the blockchain space, so surely that's obvious. But as you'll see soon, not necessarily. You need to be able to create sidechains on demand. We need to be able to have multiple sidechains, not just one private chain. And also, it needed to be organisationally aware. So an organisation might have, like, say, 4 nodes or maybe 8 nodes, not just one node. And most of the protocols in blockchain space at the moment are just node-based. And so they assume one node is one organisation. But invariably, you've got, say, 2 data centres that you're running, and you've got 2 racks within each data centre that you have have computers running in. So if you have to, say, reset one of the racks, you've still got a node running in that data center, which is electronically close to some other server that you're running, which is the actual application. So invariably, everyone runs 4 nodes, at least. And so you need to have any protocols that you're doing, or sidechain protocols, need to be organizationally aware. And of course, you don't want to be doing proof of work, you want to be doing proof of authority, and you need to obviously be encrypting the state. So all the information you're storing on disk needs to be encrypted, as does the communications. Networking via proxies is an interesting one. Who works in a bank? Insurance company? Big company? Come on, Matthew, you work in a big company, deals with 140,000 people. Yeah. All right. So if Matthew has a computer in a DMZ and says, hi, I just want this to be able to connect to anything on the internet and have anything connect to it, the IT security people will go, and that's ditto for banks. So if you have some blockchain node and it needs to do peer-to-peer communications, it gets a bit complicated. And what they really want to do is they want to have a whitelist of, say, 2 or 3 nodes or IP addresses that are allowed to have incoming connections from and outgoing connections too. And so, hence, you need to be able to really do all your networking via proxies and not via the normal network. Off-chain communications is something that is needed as well, and we should always remember decentralization. For those people who weren't here in the first talk we did about 3 months ago, I said architectural and political decentralisation are very important. And whenever you're coming up with a solution, it's got to do those. Otherwise, it's not really blockchain. So this slide, some people hate this slide and some people love this slide. People who write academic articles and, you know, they generally don't like this slide because it should have ticks and crosses, and at the end of the day, it feels more marketing and sales than engineering and technical. So certainly when I'm doing a published paper, it's not going to have smiley faces and it's going to be a little bit more analysed. But what it tries to show is, though, like I listed out some of the aspects that I've talked about, some of the requirements that we're trying to meet. And then I looked at, say, quorum, and I looked at, you know, Hyperledger Fabric, Quarter, and others, and just to try and see how they related with these requirements. And for that matter, you might say Plasma and Sharding, they're not even privacy solutions. And the reason why they were there was because people were saying, well, can't we just do this with Plasma? You know, Plasma's coming along. Why are we trying to do this thing when we could do it with Plasma? And so Plasma, they don't worry about no permissioning or API permissioning. And there's a whole lot of other things that they're just not even, you know, it's just not within the scope of what they're doing. For Quorum, they don't have a shared state. And, you know, so on the private side, you could have multiple nodes and that are on the same, essentially the same contract, but they may not have the same overall state. So Hyperledger Fabric actually has a lot of ticks. But, you know, again, it doesn't meet all the criteria, nor does Quarter. So I've, you know, just done it, you know, like A or B, you know, good or bad, but it's not really like that, is it? You know, it's probably in the middle, and for that matter, some of them are actually probably extremes of really unhappy and really, you know, quite cool, really good. So, you know, it gives you a feel, though, that none of the existing solutions quite meet the mark, and so we need to, or I need to come up with something better. We need to come up with something better to give us Ethereum private side chains. And so there are a lot of requirements. I've got a few solutions. I'm going to talk to you about one of them. So to establish a side chain, you remember when I said, oh, I want to set up a side chain with Scott and Yang? Well, you need a way of doing that. And so if you had a smart contract sitting on mainnet and you had an organisation or set of organisations that did KYC, so know your customer, and it could link that, you know, Scott is that guy just over there. He's got scott.com as his domain, and his Ethereum address, so his key is this, and link those three things together, then he could have an entry in an Ethereum registration authority. And so that could point to either his delegate Ethereum registration authority or his organisational information, which then has key value pairs. So let's have we've got a root Ethereum registration authority. So you've got example.com and bank.com in it as an example. And example.com has a delegate Ethereum registration authority. So it's got, you know, 3 subdomains that it lists in its Ethereum registration authority. And off sc.example.com, it points at an organisational info, and that's got a key value pair. So it's got information about nodes and their e-node addresses for the sidechain. And so you can imagine that you could use that information to set up a sidechain. And as well, though, you could have more than one root Ethereum registration authority as well. And you could list in multiple Ethereum registration authorities. You don't just have to list in one. And a sidechain client, it could choose which root Ethereum registration authorities it decided it trusted, and it could then ask them, hey, I'm looking for sidechain.example.com and bank.co.uk, and it could then go from here to there to there and here to there to then be able to get the information for all the domains that it actually wants to connect to. And so it could get the e-node addresses and keys and whatever other information it needs. And So these org info contracts, I think, are actually quite powerful. They're really simple, but the idea is you've got a name and value pair, and we could have them in reverse domain format, so com.example.somevalue.something, and so that name could match something, and it's a signed thing. You know, so Scott has signed some information and he's put it out there, and some other company has done KYC to link that information to him. So then your company could then publish some information. So at the moment people publish stuff on DNS, but because DNSSEC is not widely deployed, then you're not guaranteed that you really can have secure information easily available to you. Whereas this would give you that information, that ability to publish your own secure information, and you could have name-value pairs in a globally unique format. So I think it's very powerful. And for instance, say if we're looking at our sidechain piece, because this is the reason why I've created it, was you could have, so we've got pegasus.tech is the name of our domain for our group within ConsenSys. So you could have tech.pegasus.scnode.size. So how many sidechain nodes do I have? And then you could have, say, other keys that are tech.pegasus.sidechain.node1.enode address. And then, so the value for the enode address could be a string. And so that would allow you to look up that information from, for your company. And it would be your information about your network nodes for your sidechain. So that was a very brief view of what is, a massive amount of work that's got all those requirements to meet. And so thank you very much. And so Rob Dawson, who's playing with his phone there at the back, because he's seen a lot of these slides before, has got 2 t-shirts that he is going to very quickly come to the fore, and we're going to say thank you to our 2 guests here. And I've already got enough t-shirts, so I'm all good. But whilst Rob is looking for them, so we're going to have another session on October the 31st. And what we're going to do is, I'm going to put the effort in to find someone at QUT to represent QUT. There is going to be someone who isn't myself from University of Queensland, and we'll either KB or maybe a different researcher from Griffith University will come along and will provide you what is the latest research in that time. And also next week we're doing Solidity programming, and Lucas Cullen is going to tell us all about that. So are there any, let's do the t-shirt. So there is a new t-shirt. And KB, thank you very much. So KB's come up from the Gold Coast. Thank you very much. Thank you very much. Thank you very much for coming on. And are there any questions about anything that either I or the other 2 speakers can answer? Okay. Oh, yeah.
Is that just an example, or is it somehow related to the Pangea project?
Oh, the one that I just did?
Yeah.
It was just some example that I came up with. All I wanted to do was have it reading cross-chain and writing cross-chain, and writing another node to join the chain, instantiating the chain on the fly, deploying a contract. So that was just an example. It wasn't based on reality.
Yeah, but I like the table because I would have asked otherwise why sharding or plasma wouldn't have solved the problem, but the table showed where the missing features are.
Yeah, well they're solving very different requirements. I mean, I'm not worrying so much about gas, I'm not worrying about ether, and so they've got a lot of their crypto incentivization that they've got to worry about that I don't have to worry about, but then they're not worrying about permissioning, and we've got permissioning, and so permissioning is a really hard problem. And also all of their nodes know about everything, whereas here, not all nodes, only some nodes are involved in communications or in each sidechain. So there are different complexities, and they're solving quite different problems. Okay, look, thank you everyone for coming along, and see you again in 2 weeks' time.